Hey everyone, my name is Jeff Duffy and I am a product manager for Amazon DynamoDB. I'm going to be joined a little bit later by Somu, our engineer for Amazon DynamoDB. And I'm here today to talk to you about an exciting new feature that we've just released in preview called multi-region strong consistency for Amazon DynamoDB's global tables feature. And so I'm going to start by talking about how Amazon DynamoDB's consistency model works today and why this new feature gives you additional capabilities. And then I'm going to talk through some multi-region strong consistency use cases and where this might fit some of your workload needs. I'm going to do a really quick demo of showing you how to create an MRSC table in the console. And then Somu is going to come and do a deep dive on how we built multi-region strong consistency and give you a demo of how the behavior works compared to our eventually consistent global tables. So DynamoDB Global Tables is a feature that provides multi-region, multi-active replication. And so what that means is that you can have replica tables, two or more constitute a global table in different AWS regions, and you can write to and read data from any replica in the global table, that is any region, and we will replicate changes to all of the other replicas in the global table. And this allows you to increase your availability target for your applications from 4 nines from keeping your data in a single AWS region to 5 nines by having a global table with your data in 2 or more AWS regions. Global tables will also let you store your data where it's used and where your users are, so you can get some better performance by reading data closer to where the application is. And it's really easy to use, as you're going to see in a moment. You can simply take a table, you can add replicas to it in any region that you like, and we'll automatically take care of all of the replication for you. So the new feature that we're releasing is multi-region strong consistency, and we're releasing this in preview today. And this is going to let you build globally distributed applications that have a recovery point objective of 0. And we define recovery point objective, or RPO, as the amount of data that you're willing to not have access to should you need to shift application traffic from one AWS region to another because of some interruption. So let's take a look at how consistency works in DynamoDB today before this feature was released. And we're going to start by looking at the scope of a single AWS region. And so in our example here, we've got a table in the US West 2 region, and we're going to do a write to it. We're going to change some data, so we're going to call the update item API, and that data will change in that single region table. And then when I read the data with a get item call, that is by default eventually consistent. And what that means is that it is possible for you not to see the result of the change that you just made with the update item call. Your data can be stale. It is eventually consistent. Now, if that's not okay for your application's needs, we can use strong consistency in this single region scope instead in order to make sure that you're seeing the latest changes. And so in this example here, again, my single region table in US West 2, and I'll perform that update to the item. And when I perform the get item call, I'm going to pass a parameter called consistent read and set it to true. And what this does is that makes that read a strongly consistent read. And we support strongly consistent reads for our read APIs in general. And that means that you're always going to get the latest version of the data. You know that you're going to see the change that was made in update item. So then what does that look like when we move from a single region to a multi-region scope? So in our example here, I now have a global table. And that global table has replicas in the US West 2 and the US East 1 regions. And the replication between them is the default replication that we have today for global tables, which means it's eventually consistent. And so now, if I have some users on the West Coast who perform an update item call to the US West 2 replica, and then they perform a get item call in a strongly consistent manner, setting that consistent read parameter to true, they know that they're always going to get the latest version of data as long as that data was updated in that US West 2 replica. But if somebody updated the same item over in our US East 1 replica, then they could get stale data because our replication is eventually consistent, typically taking single-digit seconds depending on how far apart the regions are that the replication is occurring between. And so the same is going to be true for our users over on the East Coast, right? They're going to do a get item, they're going to do a strongly consistent read, and they'll know they'll always get the latest version of the data over there on the US East 1 replica. But again, if somebody changes the data, the same data in US West 2, maybe they haven't seen the changes yet when they perform their strongly consistent read. And so this is fine for a lot of applications. We have a lot of customers that are building a lot of really cool stuff, and eventual consistency is just fine for what their applications need. But what if it's not good enough? And the answer is to look at multi-region strong consistency, which is the feature we're offering now in preview. And so the change here becomes the replication type. Rather than replicating eventually consistent replication between the two regions, we perform strongly consistent replication. And so again, our global table example here in the US West 2 and US East 1 regions, but now it's configured for multi-region strong consistency. And so now, when my users on the West Coast perform an update item call to that US West 2 replica, and then they do a get item call setting consistent read to true, that strongly consistent read, they know that they have the latest version of the data no matter where that data was updated. Even if somebody updated the same item in US East 1, they're going to see the change immediately. And the same, of course, is going to be true in any replica in a strongly consistent global table. Anybody at any time can do a strongly consistent read and know within a multi-region scope, that data is always the latest version of data. And so here's a comparison between the two modes for global tables. On multi-region eventually consistent tables, which is, again, the default in our production offering today, we're going to tend to see lower write and strongly consistent read latencies because our writes and reads are only operating on the replica in that local region. They don't have to consider changes that are made to any other region. But the trade-off there is that, again, their strongly consistent reads can return stale data. And so we have to figure out what do we do if somebody updates the same piece of data in two different regions at the same time? How do we resolve the conflict that can result from that? And in multi-region eventual consistency, we use an approach called last writer wins, which means from the timestamp wall clock, whatever the actually last accepted update was, is the one that the rest of the global table eventually converges to. And so what that's going to mean is that our recovery point objective is typically going to be measured in those single-digit seconds. Again, depending on how far apart those two regions are. It's basically how much time does it take me to take changes from one replica and replicate it to the replica that you're reading from for your failover target. But with multi-region strong consistency, one of the trade-offs that we're going to have to make to get that strong consistency is that our writes and our strongly consistent read latencies are going to tend to be higher because we have to consider making sure that any change in any replica in any region is going to know that we're going to see that data, that version of that data. But strongly consistent reads in a multi-region strongly consistent table will never return stale data. You always know you have the latest version of it. So our conflict resolution has to work a little bit differently here because if we adopted a last writer wins, then we could get out of sync with respect to what the true consistency of the data in the table was. And so we don't use that approach for multi-region strong consistency. Instead, what we do is that if you do a write to two regions at the same data at the same time, the latter write, the one that happens just a little bit later, will detect that another region is modifying that item at that time, and it's going to return an error to you. And so we've introduced a new exception in our API. It's called a replicated write conflict exception, and this is safely retriable. If you try to do a write and you receive this exception, you know somebody else is modifying the data, you can go ahead and configure your application to retry again until it succeeds. And one of the major upsides then, of course, is that our RPO is now 0, right? I never have to think about how long replication takes and data consistency when I'm building my high availability strategy because I just know the data is always going to be there and it's always going to be correct. And one thing I'd like to call out to dispel some confusion, regardless of the mode of global tables that you're using, eventually consistent reads are always eventually consistent. That doesn't change whether it's a single region table or a global table, and it doesn't change whether you're using eventual or strong consistency in the global table. So let's look at a couple of use cases, right? So the primary reason most customers adopt global tables is to increase their application availability, their business continuity profile. And so what they'll do is to set up a global table. And in my example, I've got an application, and it's primarily reading and writing to the replica in the US West 2 region here. We, of course, replicate our data in an eventually consistent fashion over to US East 1. And that user knows that they've got a copy of their data sitting somewhere else, safe, should they need to go process data elsewhere. And so in the event their application fails and they say, oh no, I need to go transfer all of my traffic over to the US East 1 region, easily done, right? We can spin up our application, we can point to the data that's been replicated. But again, RPO, single-digit seconds, because it's taking time to replicate data over to that US East 1 region. And if there was an interruption in network connectivity between these replicas, then there might be data waiting to be replicated back in West 2 that you're just not going to see in East 1 until that connectivity is recovered. But with strong consistency, some applications can't tolerate that. So for instance, customers in the financial industry who are performing financial transactions can't tolerate the idea that should they have to shift traffic to a different region, some credit card charges might not show up. That's not acceptable. And so with multi-region strong consistency, that's not a problem anymore. Because what we're going to be able to do is to say, hey, if my application fails and I shift traffic to US East 1, my RPO is 0. I'm still getting everything that got changed in any region immediately when I read it. I talked a minute ago about the other primary reason that customers use global tables, and that is data locality, the idea that I want to get my data closer to my users so I can read and write to that data faster. And as you can imagine, because reads and writes in an eventually consistent global table are only operating in the local region first and then replicated to other regions, we have very good low latency profiles for reads and writes in that region. But again, that trade-off is data can be stale. I can do a consistent read and maybe something that changed in another region doesn't show up here yet, and I don't always have the latest version of it. But again, with strong consistency now, that's not going to be the case. With a multi-region, strongly consistent table, always getting the latest version of data when I perform a strongly consistent read. The trade-off being that higher write and read latencies that I talked about compared to eventual consistency. And that doesn't mean that this is useless for getting data closer to your users. In fact, I expect to see customers adopt this model when they can tolerate some eventually consistent writes, and they'll just do eventually consistent writes to the multi-region strongly consistent global table, and those are going to be lower latency. So some of the things I'd like you to consider when hopefully you'll give this a try and see if it is appropriate for some of your workloads are these. First of all, this feature is in a public preview. It is not appropriate for production use today. Of course, once we become generally available, we hope that you will adopt it for your production workloads. But again, today, please just kick the tires, test it out, see what you think. Replication consistency, it applies to the entire global table. You configure it when you create the global table, and you can't mix and match replicas within a global table. So if you have a multi-region, strongly consistent global table, that means every single replica in it participates in strongly consistent replication. And you can't change after you create the global table. You cannot switch back and forth today. There's kind of a multi-step process where it's possible to go from a strongly consistent global table to a multi-region eventually consistent by deleting all the replicas, leaving a regional single region table, and then building a multi-region eventually consistent global table from that. But as of today, there's just no switch where you can go back and forth. And our preview, as most previews are, has a few limitations compared to where we plan the generally available product to be. And so one of those is that we support 3 regions for the preview: US East 1, US East 2, US West 2, and we require that multi-region strongly consistent global tables be deployed to all 3 of those regions when you create them. And so now I'm just going to do a quick walk through. Well, I was going to give you a live demo, but of course it logged out. Some of you want to come up and get me into the machine? Awesome. It's live demos, right? That's why we do them. Cool. So here's the Dynamo console. I have a table here called MRSC demo. This is an empty single region table, and I can prove that I'm not fibbing by looking at the replicas in the global tables tab. No replicas. It's just a single region table. And so I'm going to create a multi-region global table by clicking on the create replicas. And now I'm going to get choices for the consistency mode for my global table that I want to configure. We'll go ahead and choose strong consistency. And you'll notice that when I do that, I'm going to automatically choose the replication regions for you because, as I said, for the preview, we operate in 3 regions, and we need exactly 3 regions, so I'm not going to make you choose. I know what they're going to be depending on which region you're acting from. And I'll go ahead and hit Create. And this is in the background going to go do its thing. And then, because I don't want you to have to wait for that to actually create it, it takes a minute or 2 for us to go set up the replicas and start replication. I'll just go ahead and click on this pre-prepared one that I had before. And you'll notice 2 important things. First, I've got 3 replicas here in my multi-region strongly consistent global table. And the other is that I now show the consistency level as strong for the global table. And that's how you can tell the difference between them should you create a few and want to go play around with it and try it out. And so now I want to invite Somu up on the stage to talk to you in detail about how we created this feature. Thank you.
Thank you, Jeff. Thank you all of you for being here. I know it's afternoon. I hope you all grabbed some coffee. Show of hands, how many of you use Dynamo today in production? Wow, that's a lot. And I can see still with the bright lights on. That's good stuff. So I am here to talk to you today about the differences between asynchronous global tables and multi-region strongly consistent global tables. And I keep switching these terms, so it's eventually consistent global tables, which I refer as asynchronous global tables. And for the multi-region strong consistency global tables, I'll refer to them as MRSC global tables. There's a lot of words to say. I'm actually glad Jeff was able to get through that stuff. Specifically, I want to talk to you guys about how the underlying replication engines differ and how these 2 global tables behave in case of a regional service disruption or a network partition, because this is exactly why a lot of people deploy global tables, which is disaster recovery. And on the day when a particular regional service disruption happens, you want to fail over to the new region and have a high availability. I'm also going to talk about how we gain confidence in the protocol and the replication engines, and also talk about how you can gain confidence in the replication engine, and how you can gain confidence your applications will work in case of failures. Before I get started, though, I have a quick demo. And let's see. Actually, never mind. I think we got to go through this one. So before I get started, I wanted to do a quick demo. For the demo, I'm going to use 2 identical global tables across US East 1, US East 2, and US West 2. They're, in fact, going to have identical key schemas, and they have only 1 item each in each one of the global tables. And the purpose of this item is to just count the number of attendees at reInvent, right? Like, it's just a toy program. The only difference between the 2 global tables, as Jeff mentioned, is one of them has multi-region consistency set to strong. The other one doesn't have one. By default, it's eventually consistent. And we're going to run through 2 experiments for this demo. One of them is going to be a multi-writer experiment, where we're going to write concurrently to the same item across from multiple regions and observe what the values are. And in this case, it's just going to be incrementing the counter. Let's assume that everybody is checking into reInvent, and we're going to be incrementing the counter in all 3 regions, and we're going to see what the difference is. The second experiment is going to be to demonstrate how strongly consistent reads work for both these versions of global tables and how they differ in terms of strongly consistent reads. So we're going to write to only one of the replicas, but we're going to issue a strongly consistent read and an eventually consistent read from the other 2 replicas and see what the values are. So this is my setup. It allows me to select the table I want to kind of use and the experiment I want to run. The iteration count is the number of writes I want to do, or the number of increments I want to do. So I'm going to reset this counter, reset it to 0. And then I'm going to run the first experiment, which is a multi-writer experiment with the asynchronous global table, which is the async GT. So right here, I have some latency analysis with 5 iterations. It's not much, but what it gives you is a rough estimate of how quick it is to reach US West 2 from Vegas. Right? It's the closest available region. And you can see the write latencies for US West 2 is really, really low compared to the other 2 regions. And you can see that each one of the regions and replicas have operated independently. And while updating the values 5 times each, they kind of keep updating the values from 3 to 4. Then you see US West 2 going from 2 to 3. And eventually, they converge at 4 to 5 which is basically everybody kind of incremented their own values without seeing what the value on the other replica was. And this is how asynchronous global tables works. It is meant for high availability use case and really low latency. We're going to rerun this same experiment with the MRSC global table. We're going to reset the counters because I think I've been playing around with this for quite some time now. And we're going to see what the latency looks like. So take this latency with a pinch of salt because this is running from my laptop. But the US West 2 latency is definitely higher than the other two. US West 2 latency when we ran with the asynchronous global tables. And there's a reason for this, and we'll revisit this reason later in the talk. But you can see that the values which are getting incremented for the counter are globally consistent, right? You go from 0 to 1 in US East 2, and then go all the way up to 5 to 6, and then US East 1 increments it, and then there's an increment which happens to US West 2, and eventually you land up with the value 15. So this is a globally consistent increment. So this is how multiple writers can increment the counter. A key thing to notice here is in the latency is that US West 2 had a latency of P100 of about a second or so. And this is because of something Jeff mentioned in his talk, is that when there are concurrent writers, we land up throwing replicated write conflict exceptions, and this can lead to the client retrying the concurrent write. The next experiment we're going to do is see how strongly consistent reads work with asynchronous global tables. Here, we just incremented the counter in US East 1. US West 2 and US East 2 were just observing the values, right? They were doing a strongly consistent read and eventually consistent read. So US East 1 chugs along, and we increment the value, and we're observing the value from the other two regions. As you can see, even though US East 1 has finished incrementing the values, the other two regions have still not observed it, because sometimes replication can take a little bit of time before it reaches the other two regions. And I observe the reads for about 700 milliseconds from those two regions, but it's very rare that I get a latest value. But you can see here that US East 2 has got value 2 from US East 1 because the value got replicated. But still, I think the values in US East 2 are still 0 and 0, which basically means that the values have not got replicated yet, or your strongly consistent reads in these regions are still looking at the local values. We're going to run the same experiment again with the MRSC global table. You can see the writes have very similar latencies to the reads in US East 2. But as and when US East 1 is increasing the values, you can see the strongly consistent reads in the other two regions start picking up the values of the counter, right? And you can see when as the value increases all the way to 5, all the regions catch up to the value of 5. The strongly consistent reads observe the latest value of the write from the other regions. I'll explain how all this works with MRSC global tables in a bit. So a quick show of hands, how many of you know how DynamoDB regional replication works? Oh, that's good. So this is a good primer. So I'm going to go through a quick primer of how DynamoDB regional replication works, because it's very relevant to how multi-region strong consistency global tables work. When a DynamoDB tables are scaled by partitioning them into contiguous key ranges, and we call these partitions. Each one of the partition is replicated into three different availability zones, and this is because we want high availability and high durability, right? And we use a version of multipaxers to replicate data between these three availability zones. So when a write comes in, the write is authenticated, we do the admission control checks, and then we send the write to the leader replica of a partition hosting that particular key or that particular item. The leader replica generates a write-ahead log, which contains the old image, the new image after applying the request, and then replicates it to the other availability replicas in the other availability zones. And once this is replicated and 2 out of the 3 replicas reply, we send back the result to the customer saying, hey, your write is successfully stored. This write-ahead log is the bread and butter of everything we build in Dynamo. That includes things like backup restore and update streams. And this is super important because these are 2 building blocks for our asynchronous global table replication. So the asynchronous global table replication engine does nothing but reading the update streams of all the customer rights in a region, source region, and replicating that to the destination region. In practice, when you have a global table with n replicas, like 3 replicas, like in our example, you would have n-1 replication engines. And the reason for this is we placed heavy emphasis on availability of the replication for global tables. And if we had a single replication engine, then a failure of a single region could stall the whole replication pipeline for us. In fact, we go down to actually restarting the replication every 5 minutes from each one of the replication engines to ensure that even host-level failures do not affect any availability of the replication across these regions. Now, replication is bidirectional across all these regions. And a key thing to remember with asynchronous global tables, and this is very relevant when we talk about the failure scenarios and how we handle it, is that the replication engine only replicates customer rights originating in a region. Because you have replicated rights going through the same channel as customer rights, we don't replicate those replicated rights. We just replicate only customer rights. Now, this is a time series view of how the replication looks for an asynchronous global table. Here we have 5 regions, R1 through R5, because for asynchronous global tables, you can add as many regions as you want. In fact, I see some of our internal services adding up to like number of regions we have, which is in the upper 20s. But here we have, for this example, I chose 5 to just show how the replication works. So here we have region R1 through R5. There's a write to region R1. The write is acknowledged back to the customer, and then the replication engine just picks it up and then replicates it asynchronously to all the other regions. The reason the asynchronous part is important is it's not guaranteed all the writes reach all the regions at the same time. The writes can reach the regions at varying time. And a big reason of this, for one of the big reasons is speed of light. The other reason can be that we're just recycling the lease and a new host is picking up the lease. So there can be gaps in how the replication works. Now, this becomes very relevant when you do strongly consistent reads. If you're doing a strongly consistent read in a region where the write happened, then you will see the latest value. But if you do a strongly consistent read in a region where the write did not happen, then the version of the item you see depends on whether the replication has happened or not. In our example here, R2 will not see the latest version of the read item, but R3 will definitely see the latest version of the item because the replication is done. Now, how do we handle write conflicts, concurrent writes to the same item in all regions? So like I said before, each one of the regions will accept the writes. There's no coordination between the regions. They all operate independently. And they will replicate it to the other region. And then we use the last writer wins conflict resolution to decide which one of the items should we keep and which one of the items should we overwrite. But how do we do the last writer wins conflict resolution? When DynamoDB receives a write request for a particular global table replica, it stamps this write request with 2 pieces of metadata. Metadata is stored as an internal attribute which is not visible to external customers or external applications. And the 2 pieces of metadata is what is the source region in which the write was written and a timestamp at which the leader replica received this write. And this timestamp is got from timesync service. Right. And we write the data to all 3 replicas regionally. And we write this same data to also the update streams. The replication engine, being a DynamoDB service, is able to read this metadata and replicate it to the destination regions. And once the destination regions receive this write, they're able to compare the timestamps with the timestamp on the item locally stored, and then decide which one of the writes should be persisted. If the timestamp is lower, it's going to reject the write, saying, hey, I already have a version of the item which has a greater timestamp. And if the timestamp is higher, then it's going to accept the write. But what happens if the timestamps are equal? If the timestamps are equal, that's when the source region plays a tiebreaker part in breaking the tie between the 2 writes. Now, how do asynchronous global tables behave in case of failures? A big failure is regional failure, where you have regional service disruption, or there's something else going on with the region. then in that case, the replicas in the other regions are still highly available. And this is the beauty of asynchronous global tables. All the regions operate independently. Right? The performance is equal to the low performance, and the replication is outside the critical write path to the region. The region which has failed will recover once it recovers from the failure, right? It will catch up to all the writes. In case of a region isolation, all regions are still open for reads and writes, including the region which is isolated, network isolated. And this is because it does not depend on the replication still. However, the reads in the region which is isolated may serve staler version of the items because it's not caught up to the writes which have happened in the other two regions, and vice versa. A network partition in case of asynchronous global tables, again behaves the same way a network isolation works. But the slight difference in this case is that it's only the writes between the two regions which have network partitioned that are not readable in the other two regions. Right? Once the network partition recovers, the writes are reconciled using the last writer wins conflict resolution. Now, a lot of applications fit the bill of asynchronous global tables because it's highly available. It's a one-click add of a replica, and you have a replica in another region. It fits the disaster recovery. It works very well in terms of performance. But still, there are applications out there which need to be able to read their own writes from any region and any region. So a lot of our customers went ahead and built design patterns around this stuff, such as single reader-writer region. While this works in most cases, the downsides of this approach is the latencies of the strongly consistent reads, which are routed to the writer region, are going to be dependent on where the end application is and where the writer region is. It's also, in case of regional failure, the application has to perform a failover, which is a big thing. So now you lost the whole advantage which asynchronous global table gave, which is being multi-active in all regions. Even in that case, on a failover, you're not guaranteed that you've caught up to all the writes from the region which failed. Some applications used quorum reads to kind of solve through the problem of not having a single writer region and having multi-active. But this kind of also has the same downsides as the previous approach, where the latencies of the strongly consistent reads are high, and also, in case of a region failure, you wouldn't get the latest writes. So we went ahead and built multi-region strong consistency global tables to do the undifferentiated heavyweight lifting of being able to read your own writes, even in case of regional failures. So what did we have to do to build multi-region strong consistency global tables? We have to ensure two things. One is the writes are highly available. When I mean highly available, I mean they're highly available even in case of a single region failure, which accepted the write. Two, a strongly consistent read is correctly able to serve the latest write, which has been accepted by DynamoDB across any region. So how do we do this? We use the same building block, which across all database services for building multi-region strongly consistent databases. So we use something called as a multi-region journal. And what is this multi-region journal? The multi-region journal is just a set of logs across the regions the global table spans, the MRSC global table spans. All MRSC global tables today are 3 region specific, so the multi-region journal also spans 3 regions. And this log is an append-only log. When you write a log to this MR journal, once it's accepted by 2 out of the 3 logs, a success is returned back to the writer, plus this commit callback is also issued to the other listeners in the other regions. Right? Now, when we kind of do a write, the write is appended to the multi-region journal first. The write request comes in, it's appended to the multi-region journal first. And then once the multi-region journal says, yes, it's all success, it's been appended to the multi-region journal, we kind of apply to the local DynamoDB table. Not only that, the other 2 regions which are also listening to this particular multi-region journal for all the write requests would pick up the write requests and apply it to their local DynamoDB tables. Good. What happens when you get concurrent writes? This is the most interesting piece. The multi-region journal, being an append-only log, would serialize two concurrent writes which happen to the global table. So two regions may have two writes which happen to the same item or different items, but they're both appended to the multi-region journal. And the multi-region journal acts as a serialization log for us to sequence these two writes. In our example here, the write to B is shown to come a little bit later than write to read A in region 1. But the write B gets appended to the log first, and then the write A. All the regions need to apply the writes in the order they receive the commit callback from the multi-region journal. So region R1 would have to apply the write which happened to A first before it can apply the write which happened to B. And this is necessary to guarantee correctness. Strongly consistent read in a region where the write happened is very easy to reason about because that's where the write happened. So strongly consistent read is going to kind of return the latest version of the item. A strongly consistent read in a region where the write did not happen is the one which is tricky to answer. It's like, how do I know there are no writes which are acknowledged in the other regions which the customers have got an acknowledgement for? We use a technique called heartbeating to the journal. In this case, region R2 is going to heartbeat to the journal saying that, hey, do you have anything for me? Have I missed any writes which I have not seen so far? And as a part of the commit callback, it's going to have to catch up to all the writes it did not see in between the last write it saw and the heartbeat. And this forces region R2 to take all those write requests and apply them to the local DynamoDB table, and then return the value of the strongly consistent read. So now what we've done is not only have caught up region R2 to all the latest writes, but we've also serialized the strongly consistent read with a write that might be happening, and we might return success to the customer before the strongly consistent read returns. We do use this heartbeating technique even in case of a strongly consistent read which happens in the region where the write happened. Right? So you would see the strongly consistent reads taking a little bit longer because this heartbeat needs to at least be persisted in two of the three logs of the multi-region journal. How does this look on a big picture architecture? How does the write request work for DynamoDB when it comes in for a multi-region strong consistency table? When a write request comes, it's sent to a GT shard processor. The GT shard processor then reads a local DynamoDB item, takes the operation, converts it to an idempotent write request, and then appends it to the multi-region journal. The multi-region journal then sends callbacks to all three GT shard processes in each of the regions which are listening to the multi-region journal. Once the callback is received on the GT shard processes, they just take the write request and apply it to a DynamoDB table. I said idempotent writes, and this is a big part of Dynamo multi-region strongly consistent table. What does it mean for a GT shard processor to convert a write request to an idempotent request? The write request is taken, and the current item is read, and then converted into a conditional insert or delete based on what the previous version of the item is. Now, the read of the current item is a strongly consistent read from the local region. So in our demo, we incremented the counter. So increment counter was the operation. The local value being read of the item is, in this case, 5. And we again use timestamps to version items, even in MRSC global tables. So there is a timestamp there. This current item plus the increment counter is converted to a conditional insert as a write request, idempotent write request. Now, some of this might sound familiar to some of you. It's like basically optimistic concurrency control, which is based on the previous version of the item. Now, we kind of write this write request into the journal. And the beauty of this is that, one, the idempotent request ensures that if the GT shard processor crashes after applying the write, when it's reapplied, there is no effect. Two, if there are two concurrent writes happening in two different regions, the write requests are serialized in the multi-region journal. And only one of the requests is going to succeed. In this case, one of them is going to return 200 because we saw an increment from 2 different regions in our first experiment. The other one is going to return a replicated write conflict exception. And when we throw a replicated write conflict exception, this is a retryable exception. So the SDK would automatically retry this exception for you and kind of redrive the concurrent increment counter exception. Latencies in milliseconds. So regions are not equidistant. Take these latency numbers with a pinch of salt. I grabbed them from what we had last time around. I have not looked at the latency numbers. Definitely, US East 2 and US East 1 are closer together. So whenever you're doing a write to US East 1 or US East 2, since we need only 2 out of the 3 regions to actually persist the write request in a log, the responses are going to be faster. The write request or a read request from US West 2 is going to be having a higher latency. And this is what we saw in our demo as well. It's because the write request has to kind of travel all the way to US East 1 or US East 2 to be persisted in 2 out of the 3 regions. So what happens in case of a region failure? Again, in case of a region failure, the healthy regions would still be able to accept reads, writes, and serve strongly consistent reads and writes. The more important thing here is that in case of multi-region strong consistency table, if one of the region which is failed is a region which is close to the other healthy region, you may see an increase in latency in your application. And this is something you want to account for because now the writes have to travel to the farthest region to get acknowledged back. In case of a region isolation, the healthy regions will be able to still serve high reads and strongly consistent reads and writes. But the isolated region is not going to be able to take any writes or reads. And this is the difference between asynchronous global tables and multi-region strongly consistent global tables. Network partition. The network partition is a very interesting failure scenario in case of MRSC global tables. And there's a reason I say this is very interesting because the behavior is slightly different from the asynchronous global tables and might differ from other databases as well. When there is a network partition, to understand how the network partition scenario works, we need to understand how multi-region journal kind of appends its log. In steady state, if I'm doing a write to US East 1, then US East 1 generates a log and tries to replicate it to US East 2 and US West 2, right? And as you can see from this diagram, since US East 2 is near, the replication log travels faster, and US West 2 is farther away. It's driving slowly. When there is a network partition between US East 1 and US East 2, US East 1 can only depend on US West 2 to accept its write request. It cannot depend on US East 2. But US East 2 will transitively get the replication log from US West 2. It takes a longer path, but it does get the replication log, the write request log from US West 2. And this is why, in case of a network partition, all 3 regions still remain highly available for writes and strongly consistent reads. And this is a big difference because we are a multi-active system, and in case of a network partition, the ability to have all 3 regions to be able to do reads and writes is a big advantage. Now, again, like in case of a network isolation, you're going to probably have higher latencies to do the reads and writes from US East 1 and US East 2, but that's a fair trade-off for having high availability of strongly consistent reads. So a big difference between how both these tables behave in case of failure scenarios. In case of regional failures, asynchronous global tables remain very highly available in the healthy regions, and likewise MRSC global tables. So there's not much difference there. In case of network isolation, asynchronous global tables are highly available on all the regions, except that the reads between the isolated region and the non-isolated regions are going to be fairly stale. The MRSC global tables, on the other hand, the isolated region is going to be highly unavailable for strongly consistent reads and writes. In case of a network partition, however, the MRSC global table, all regions are going to be available for strongly consistent reads and writes. And asynchronous global tables, the writes won't propagate between the partition regions. And that's a big difference between both these versions of global tables. Now, a big emphasis on in AWS when we build distributed systems is that we build them correct. We can, and we can assert the invariance of the system and test the correctness of the protocols. And distributed systems are really, really hard. When I joined AWS about 12 years back, then the best practice there was to start doing formal modeling of distributed systems and kind of prove the correctness of the system before we take it to production, because these are systems which a lot of applications depend on their correctness for. For MRSC global tables, we started using this new model checking tool called p-model to model the state of the protocol and prove its correctness. Now, P also provides a tool to check the correctness and the invariance of the system in production using the production logs at runtime. So that's called p-observe. So we use p-observe also to do model checking of the entire protocol. Now, there's a lot to be said about formal modeling, model checking, and mathematical proof to prove correctness of systems. But however, at scale, systems behave differently. They have different bottlenecks. And a big part of what we do at DynamoDB for global tables is to scale test the whole feature end to end to see where are the bottlenecks in the system, and how does the system behave at high scale. This covers all the edge cases which formal modeling would not cover, because formal modeling is at a smaller scale, while scale testing would allow you to test what a production workload will look like. Likewise, we do a lot of chaos testing as well. We kind of have packet drops, we have node crashes, and a lot of this chaos testing discovers edge cases which were probably we forgot to model or we did not think about. And this kind of helps us catch issues in testing before we kind of send it to production. And these two are used extensively. For global tables, however, we still, in spite of all the formal modeling and chaos and scale testing and all the things in testing, we kind of still do anti-entropy between the replicas to ensure that the replicas are constantly in convergence. And this is a key part of global tables, which happens in the background without any of the customers knowing about this stuff, and also impacting their traffic. We always kind of ensure that the replicas are converging. Now, how can you test what the impact would be to your application when there is a failure? So we've integrated with AWS Fault Injection Service to kind of introduce experiments which would pause replication between global tables. And this is specifically for asynchronous global tables. And this would allow you to pause replication between two global tables and see how your applications react to the eventually consistent reads when there is a replication pause between replicas. We'll also be integrating for MRSC global tables similar experiments so that you can test failures when there's a global table failure or there's a replication pipeline failure, how your applications would react to that. So we have now two versions of global tables, one which support eventually consistent, and one which is strongly consistent. Each one of them have their own trade-offs. Applications such as checkpointing your video streams is very well suited for like asynchronous global tables, because you can fail over, if there's a regional disruption or there's a failure, you can fail over to a new region and afford to lose the last 5 minutes of checkpoints. And the checkpoints are really fast, right? So it's super easy to kind of use asynchronous global tables for that. And you don't need any universal ordering in such applications. But for applications such as, let's say, a subscription application or somebody filling a prescription application where you need strongly consistent reads and you need universal ordering, and the application is willing to make the trade-off between latency and strong consistency, then MRSC global tables is the feature which you should be using. That's it, and thank you.